Hello everyone. Today we will discuss about adders. Adders are digital combinational logic circuits in electronics, and these implements addition of the binary numbers. In many computers and processors, adders are useful to calculate the countings and also addresses. First we will define the half adder. A half adder represents two single bit addition, and here we obtain 2-bit outputs. Now see here a block diagram for the half adder. Here we have the two inputs A and B as a single bit, and here we are obtaining the two output, one as a sum and other as a carry. Now we can make a truth table for the half adder as these are the inputs A and B. This is the sum of the two bits and it is carry of the two bits. Now when the first input is 0 and the second input is 0, then you know that 0 plus 0 is equal to, in binary addition, it can be written as 0 0. So here sum will be written as 0. This bit will represent as sum, let us say, and this will represent as carry. So sum of the 0 plus 0 is 0, and here carry is also 0. Now the next inputs are 0 and 1. See here 0 plus 1, it will be equal to 1. So we can write it as 0 1. So here your sum will be 1 and carry will be here 0. Now next inputs are 1 and 0. So 1 plus 0 will be equal to 1 again. So we can write it as 0 1. So your sum is here 1 and carry is here 0. Then we have 1 plus 1. So we can write it as 1 plus 1 will be equal to 1 0. So it is like in decimal 1 plus 1 is equal to 2. So here in terms of the decimal number, this binary number will have the weightage 2. You know it because it is one column, it is two columns, so its weightage is 2. So here your sum is here 0, so you write here 0, and your carry is here 1, so you write your carry is here 1. Now if you take the output of this truth table, then you can write in it in terms of the SOP form. So you know that your sum, you are getting two outputs 1 and 1. So for sum your output will be A bar B plus A B bar, or you can write it as A exclusive B. For carry you obtain one output, this is your A and this is your B. You are obtaining output 1 here. So in SOP form it will be written as A B. So these are the two outputs for half adder, and we are using two single bits A and B as inputs. Now this is the equivalent logic circuit of the half adder, because as a sum we have the exclusive OR gate. So this is your exclusive OR gate, and as a carry you have the AND gate. So it will be your AND gate and it will be represented by the carry output, and it is sum as a output, and it is equal to A exclusive B. Now this is very important, that how we can implement of half adder by using minimum number of 2 input NAND gates. This is basically a 1-3-1 system for your remembrance. Now you see here that we have used here a NAND gate, and there are two inputs A and B. When we get here your output through this NAND gate, you know that the output will be AB bar. Now there is the other NAND gate, and for this NAND gate you have one input as A and the other input is the output of this NAND gate. Similarly here you have a NAND gate. One input of this NAND gate is the output of this NAND gate and other is the B input. So when you obtain the output after this NAND gate, it will be like this is your A and this is your AB whole bar input. So here your output will be A dot AB bar whole bar, and from the De Morgan's law you can write it as A, it is your like XY. So XY bar, it will be your X bar plus Y bar. So it will be your A bar and AB whole bar is already there, so it will make AB double bar, so it will be equal to AB. Now we can use here the distribution law and it can be written as A bar plus A into A bar plus B in other bracket. You can write this term as here A bar plus A in bracket and then A bar plus B. A bar plus A, you know, it is equal to 1, so it will be your A bar plus B. So here you have an input that is A bar plus B. Similarly for it you can write it as B bar plus A in one bracket and then B bar plus B in other bracket. So B bar plus B will be 1. So here one input will be that will be B bar plus A, right? And here your input will be A bar plus B. So after the two inputs of A bar plus B and B bar plus A, here we get the output that will give you an output that will be equal to an exclusive OR gate, and it is equal to A bar B plus AB bar. Similarly here after this NAND gate you are getting an output AB whole bar. So when we apply here on this NAND gate and here the inputs are common, so your output here will be as equal to AB, because this input is your AB whole bar and this input is also AB whole bar. So when you use the AND operation and then operate a NOT operation, then your output will be here AB, so it will give you a carry. So the total number of the NAND gates here will be 5, by which we can implement a half adder by using minimum number of the 2 input NAND gates. Similarly, we can implement half adder by using minimum number of the 2 input NOR gates. So this is your NOR gate. It is a system like 1, 2, 1, 1. Now see here, this is your NOR gate and it has 2 inputs. So here your output after this NOR gate will be A plus B whole bar, you know. Then you draw the 2 NOR gates. This is your one NOR gate, this is your other NOR gate. So here the one input A will go to this NOR gate and it will be a common input. Similarly for this NOR gate we give an input B and it will be common to this NOR gate. So here we will obtain an output that will be equal to A bar, because it is A and it is A, so A plus A will be A, and the note of A will give you A bar. Similarly here, this is your B, this is your B, so B plus B will make B, and note of it will make it B bar. Two inputs, A bar and B bar, to this NOR gate. So here your output will be as a carry, and it will be equal to AB, because here we will have A bar plus B bar through the OR operation. Then we will make note of it. So by the De Morgan's law, we can write A bar plus B bar as AB whole bar, and a bar of again it will give you AB, which is equal to a carry of the half adder. Similarly here, this is the AB input for this NOR gate, and this is your A plus B whole bar output of this NOR gate. Now these two will act as the input for this NOR gate, and then you will obtain output as an exclusive OR gate. You can see here that this is your AB input, and this is your A plus B whole bar. So after OR operation, you will have AB plus A plus B whole bar. Then you have the note, so it will be a note. Now we can use here the De Morgan's law. So x plus y, it will be x bar into y bar. So it will be AB whole bar, A plus B bar, and again bar, it will be A plus B. So it will be AB whole bar, A plus B. Now again, you can use here the De Morgan's law. So it will be A bar plus B bar and A plus B. So you can write it as A bar B plus A B bar, and it is equal to A exclusive B, which is sum of the half adder. So here you can see that we are using 5 NOR gates. So in implementation of half adder by using minimum number of 2 input NOR gates, we will require 5 NOR gates. Now we will define the half subtractor. It is like your half adder. Here we have 2 single bit and as an input, and then we are here obtaining 2 outputs. One is called as a difference and other is borrow bits. Now the truth table for the half subtractor is that there are 2 inputs A and B, and there is a difference output and other is a borrow output. So here you see that 0 minus 0, it will give you a 0. So here you can write as 0 0. So here difference will be 0 and borrow will be 0. Then it will be 0 minus 1. So you cannot do 0 minus 1. So you have to take here a borrow. So when you take a borrow, then it will be like your, here if you take a borrow, it will be written as 1 into 0. So in terms of the decimal number, its weightage is 2. So 2 minus 1 here will be 1. So you can write here as there will be 1 as the difference and there will be 1 borrow. So there will be, you see here, 1 as a difference and 1 will be a borrow. Then we do 1 minus 0. So it will be 1 minus 0. It is your equal to 1. So it will be written as 0 into 1. Then 1 minus 1, it will be as 0. So it will be written as 0 0. So here you see that you can write here as borrow and you can write here as by difference. It is like here you write here sum and you write here carry. So here you write borrow and Here you write difference in place of the sum as in half adder. Again, if you write the SOP form of this truth table, then you can have the outputs. So your y difference here will be, because in y difference you are obtaining two ones for the inputs 0 and 1 and 1 and 0. So your y difference will be a bar b plus a b bar, and it is a exclusive b. As a borrow, you are obtaining one output here, so your SOP form here will be a bar b, and it will give you a borrow output. Now see the equivalent circuit of the half subtractor. Here you obtain difference as a exclusive b. So this is your exclusive OR gate, and your borrow is here a bar b. So this is your a, and now we have used here a NOT operator. So it will be here a bar. So a bar will be input for this AND gate, and this is your b input for this AND gate. So here your output will be a bar b. Now similarly we can implement half subtractor by using NAND gate and NOR gates. So you can solve these as in earlier case, in case of the half adder, and your difference here will be a exclusive b, and your borrow will be a bar b. So here you see you are using 5 NAND gates, and similarly here you are using 5 NOR gates. Okay, you can solve it yourself. Thank you.